Okay, so let's get started. Remember what we're in the middle of doing. We're in the middle of doing something like the Bolzano-Weierstrass theorem, but for functions, right? For functions, and with respect to the Supremum norm. Do you remember that thing? So we defined, you have some set, right? And you have some functions. You have a sequence of functions on that set. We defined the Supremum norm. So we defined a kind of norm, right? A norm of the functions, and that norm was the supremum of the values of f of x as x ranged over E, as x ranged over that set. Right? This thing actually has a name. It's called the Supremum norm. Supremum norm. And you remember that we actually defined these only on continuous bounded functions. Continuous bounded functions, complex valued functions on your set. Okay. And what was good about this norm was that convergence with respect to this norm, right? For convergence for this thing to converge with respect to the Supremum norm, to the sup norm, it was the same thing as uniform convergence. Okay, it was the same thing as uniform convergence. Okay, so let's just recall our setting. Okay. Okay. And so what we're doing is basically asking, is there some sort of conditions that we can put on a sequence of functions so that we're guaranteed a uniformly convergent subsequence, right? Such that we're guaranteed a subsequence that converges with respect to the sup norm. Okay, so that's our goal, basically. Goal to find some sort of conditions that find conditions on a sequence of functions that guarantee convergence, a uniformly convergent subsequence, which is the same thing as saying a sequence convergent with respect to the sup norm. Okay. With respect to the metric that you get from the sup norm. Okay. And we weren't able to get, we hadn't got anything like it yet, right? We had, the last result we had was the theorem that if you have a sequence of, complex valued functions, if E was countable, and each of these guys was pointwise bounded. Then you're guaranteed a pointwise convergent subsequence. Then there exists a pointwise convergent subsequence. Hang on. Okay. You got a pointwise convergent subsequence, but that's not what you wanted at all, right? We didn't want a pointwise convergent subsequence. We wanted a uniformly convergent subsequence, right? So that we could use all those theorems that we've just proved, right? And we got all these great results about uniform convergence, right? This, we're not happy with this, okay? But this will actually prove really useful in getting the result that we want. And remember, we got this by doing the diagonal process. We had to construct that with sequences and sequences, and then take the diagonal, and that would give it to us. Okay, so there's an example in your book. So I'm not going to go through this example, but let me just mention that there's an example in the book that shows that if Fn is uniformly bounded and on a compact set and pointwise convergent, that these things don't guarantee existence of a uniformly convergent subsequence. Okay, so this is not enough, right? These conditions aren't good enough. The condition that turns out to be really key is something called equicontinuity. Okay, so this is what we need. What turns out to be necessary, in part, is this thing called equicontinuity. Okay, so let's define it. So here we start off with f, a collection of functions, and they're all from e to some to the complex numbers. Okay. So so here's the definition: if for any epsilon greater than 0, there exists a delta. There exists a delta, positive delta, such that if the distance between x and y is less than delta, then the distance between f of x and f of y is less than epsilon for all f in your collection. Then we say, we call F an equicontinuous family. On E.
Professor?
Yes.
Trivial.
Yes.
But instead of saying distance of x comma y, can we say absolute value of x minus y?
No, because this is just in some metric space. Right? So this, you don't know where this is. Right? This is in some metric space. It's a good question. Yes.
What is our collection? Is it a J or?
I'm sorry, like a set.
No, I meant the variable. Is it?
I'm sorry. That's an F.
Oh.
I don't know. I forgot how to write a cursive F after so many years. I know it's wrong looking. Anyway, that's an F. Okay, that's a capital F. Okay, so equicontinuous. So what do you think about this definition? What do you think about this definition? Given any epsilon, there's a delta such that as long as 2 points are within delta of each other, then the outputs are within epsilon of each other for every f in your collection. Okay. What is this reminiscent of? What is this very similar to?
Continuity.
Continuity? Not just continuity.
uniform.
Yes, uniform continuity. Yeah, uniform continuity, right? Right, because what is it saying? It's saying that, given any epsilon, there's a delta, and this delta doesn't depend on anything, right? Right. As long as you've got your 2 points within delta of each other, then the outputs are within epsilon of each other. Okay. So it's like uniform. If we were dealing with just one function, then this would be uniform continuity. Okay. But it's a family of functions, and so what you're saying is that there's a delta that not only works everywhere for this one function, but it works everywhere for every function, right? So you can think of this as basically uniform continuity. Right? It's uniform continuity, but that uniformity is uniform across the whole family. Okay, so just something to make sure you're awake. Any finite family of uniformly continuous functions is equicontinuous. Right. So turn to somebody nearby and say, yes, of course, or
Oh yeah, because it's fine. Each of them has it?
So if there is
Yeah, because each of them would be
each of them
one.
would say
But why can't be any maximum of the points is really epsilon. The farthest away points are within epsilon.
set.
This delta epsilon, so it should work for all of them.
Yeah, and that would go with
Yeah, but because you can't make it on.
yeah, the
Setting
farthest away.
collection.
So if you're in the delta neighborhood,
So whenever it doesn't know, then you just take.
no, I say if you're in the delta neighborhood, then you map to the epsilon.
Okay, why is it clear? Why is it simple? Why is it obvious? If you've got a bunch of uniformly continuous functions, right? So you know that given any epsilon, for each one of them, there's a delta that works, right? Can you find a delta that works for everybody? What do? Just take the minimum. You take the minimum, right? You would take the smallest delta, because then that delta would work for everybody, right? For each function, it says, I want you to be within one unit of each other. I want you to be within a half a unit. Right? The next guy says, I want you to be within a third of a unit, right? So if you take the smallest one, then that satisfies everybody, right? Then the outputs are all going to be within epsilon of each other. Okay. Right, so basically the proof is given an epsilon, take the minimum of the delta, take the smallest delta, right? And that will, then you satisfy all deltas. Okay. So we said that this was going to be the key condition to help us get a uniformly converted subsequence. So let's talk about the relation between this notion, equicontinuity, and uniform convergence. Okay. Okay. So we'll start off with the following theorem, which I may just make you do as an exercise. So suppose you have a sequence of continuous functions on a metric space K. Right, so it's going from K, these are complex valued as usual. if K is compact and the Fn converge uniformly, then these guys are equicontinuous. Then the sequence is equicontinuous. Okay, so let me break it up into pieces. So actually, you guys are still copying, so let me hold off for a second. Okay, so what do you want to show? We want to show that for all epsilon, there exists a delta such that if the distance between x and y is smaller than delta, then the distance between fnx and fny is smaller than epsilon for all n. Right? That's our goal. So, okay, right, and we have uniform convergence, right? We have uniform convergence. I'm trying to think of how to make this an exercise. Maybe I won't make it an exercise. I'll just do it. Okay, yeah, I'm just going to do it, sorry. Okay, so fix an epsilon. Okay, fix an epsilon. By uniform continuity, by uniform convergence, we know that there exists an n such that if n is greater than n, then the distance between fnx and f capital N x is smaller than epsilon over 3 everywhere, right, for all x in E.
It shouldn't be x and k. It would be
K, I'm sorry, thank you. Okay, so remember what we're trying to do. We're trying to show these guys are uniformly continuous, right? We're trying to show that these guys are uniformly continuous. And what we're saying is that, well, look, we can make, past a certain time, everybody is pretty close to this one guy, right? Everybody is basically this one guy. Okay, so this is the main idea. Everybody is basically this one guy. And who else do we have to worry about? We have to worry about everybody who precedes this guy. Right? Now, this one guy, is it uniformly continuous?
yes.
Yes. Why?
It's it's a continuous mapping over a compact set.
Exactly. Right. Each of the functions, right? So each of the functions is continuous on a compact set. So each of them is by itself uniformly continuous. Right. So notice each f sub n is uniformly continuous. Okay.
You said that's because they're uniformly convergent on a compact.
No, because they're continuous on a compact set, right? Yeah. Okay. Okay. So So here's the idea, past some point, everybody is this one function. Before that point, you have only finitely many functions, right? This guy's uniformly continuous. Everybody who precedes him or her is uniformly continuous. I don't know, I've always referred to functions as guys, but like during my qualifying exam, I'd say, so you've got this guy and blah, 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 blah. Anybody who precedes this function is uniformly continuous, and so basically you've got a finite collection of uniformly continuous functions, so it's equicontinuous, right? That's the idea, right? Okay. So you say, okay, well, my previous remark, f1 through fn is equicontinuous. Right? These guys are equicontinuous, right? And so we know that there exists a delta such that if the distance between x and y is less than delta, then fi x minus fi y is less than epsilon over 3, right? For I equals 1 to capital N. Okay. Right. So actually, let me call that delta 1. I'll call it delta 1. Recall that f sub n is itself uniformly oh, no, I don't need to call it delta 1. The delta, sorry, because I've already included f sub n. This delta works for f sub n as well. Okay. I thought I'd have to use a different delta. I don't need to. Okay, so now, so this delta works for this first bunch of guys, right? And now we just need to see what happens for the later ones, right? So for n bigger than n, right, if the distance between x and y is less than delta, then fnx minus fny, right? Well, what are we going to use? Triangle inequality, right? It's clear, right? This is, we're just going to throw in a capital N, right? So we throw in capital N x plus capital N x minus capital N y plus capital F capital N y minus F N y. Okay, so we throw in again 0 2 times. We throw in 2 zeros because we want to involve uniform convergence and uniform continuity. Right? Right? We have uniform convergence and we have uniform continuity. We better throw them in there, right? To use them. So we say, okay, well, this is, we get this term, which is controlled by uniform convergence. We get this term, which is controlled by uniform continuity. And we get this term, which is controlled by uniform convergence. Right? Right? Uniform convergence, convergence, continuity. So it's less than epsilon third plus epsilon over 3 plus epsilon over 3. Okay. Okay. Any questions? But just remember the basic idea, right? Is that these guys converge uniformly to that guy, right? And so they're basically that function. They're basically that function, right? And then you've basically got a finite family. You've got a finite family, and then that does it for you. Okay, so what we've shown is that there's a relation between uniform convergence and equicontinuity. Right? If you have uniform convergence of continuous functions on a compact set, then the guys are equicontinuous. Okay. And now we do the great theorem of Ascoli-Arzela. So I'm going to erase. Is it okay for me to erase this? Are people still copying this down? Erase this. Okay. So this is still under the heading of with the relation between equicontinuity and uniform convergence. Sort of an opposite statement, a converse statement. Not exactly. But. So if you have a sequence of complex value functions on some set K, some metric space K, if, as before, K is compact, the Fn are pointwise bounded on K, and these guys are equicontinuous. Then F sub n is actually uniformly bounded on K. And further, F sub n has a uniformly convergent subsequence. So this is answering our question. Okay, ready? Okay, here we go. So we're going to prove this in parts. The first part we'll show is that these guys are uniformly bounded. Okay. Okay. So we know that the functions are equicontinuous. Right? We know that the functions are equicontinuous. So if we set any epsilon, we can find distances so that the functions don't vary that much, right? Don't vary by more than epsilon, as long as we stay within that distance, right? We also have compactness, right? Compactness almost means that your set is finite, right? Now, right? So I don't know, are people starting to see it? Right? Your set is basically finite right? You've got equicontinuity and you've got pointwise boundedness, right? So that at each point, your collection of functions is bounded, right? Right? Well, if you've got, if you've got your set is pointwise bounded, well, at each, suppose you've got a set of finite points. At each point, your set is your set of functions is bounded, right? Then you've got a uniform bound, right? That should be enough, right? So what we have to do is manage how the equicontinuity interacts with the compactness, right? The equicontinuity and the compactness together will allow us to get the actual statement. Okay. So, right. So you say, okay, fix an epsilon, right? Fix an epsilon. That gives us a delta, right? We get a delta such that whenever two guys are within delta of each other, then fn x minus fn y are within epsilon of each other. Okay. Now we're going to use the compactness, right? So you say, okay, now cover the whole thing with delta balls, right? Okay. So cover K with neighborhoods of radius delta. Right? So every point in the set you cover with a delta ball. Okay. Compactness, right? By compactness, you know that there exists a finite subcover, so there exists n delta I1 through In that a finite subcover of K. Okay. So you've got your set, and it turns out that there's just a bunch of points, right, whose delta neighborhoods cover the whole thing. Right? The delta neighborhoods cover the whole thing. Well, the functions are bound. The functions are bounded at each point. The whole family is bounded, right? At each point, there's a bound for the whole family, right? And you know that over this neighborhood, the functions don't vary that much, right? And so you take the max, and then you add on that variance, and that's the total bound. Yeah.
What do you mean by the functions don't vary much?
Because of the equicontinuity, right? That right? As long as you stay within this neighborhood, the function doesn't vary by what the value is at the center here. Okay. So you say, well then, pointwise boundedness implies that there exists bounds mi from I equals 1 to n such that f and xi is smaller than mi for I equals 1 to n. Bad notation. There exists bounds f, let's say f sub k, right? And for any k 1, 2, 3, infinity. Right. So at each of these points, there's a bound. Right? M1, M2, blah blah blah. Right. Okay. We're basically done. Right. Then for any x and k, for any point, well, you're going to lie in some neighborhood, right? So f and f let me call it M. Sorry. I'm going to use K. Sorry. F. I'm going to use M. Sorry. Okay. Sorry. Let me use this. Let me call this M. so that I don't have to say lowercase k and capital K. So fmk, right, is going to be less than the max of the m's mn plus epsilon. Right? Right? Because fmk is going to be fmx is going to be fmx minus fmxi plus fmxi, where for some I, such that the distance between x and xi is less than delta. Right? And so we get this is less than fmx minus fmxi plus fmxi. Right? It's simple, right? You pick some x. You pick some x. X has to lie in some neighborhood, right? X has to lie in one of the neighborhoods. So there must be some xi, right? There must be some xi in whose neighborhood x lies, right? Well, the value of the function there in absolute value is smaller than mi, right? It's smaller than the value here of the function is going to be less than mi, and the difference between the values, right? The difference between the values is smaller than epsilon, right? So the value here is controlled by the sum of those things, by the triangle inequality. Okay. So that's it. We get uniform boundedness. Okay. Everybody okay? Okay. We have 7 minutes. Let's see if we can do it. So now we want to go for uniform convergence. Okay. So, right. Now we want to show that Fn has a uniformly convergent subsequence. Okay. Okay, so again, let's fix an epsilon. And again, we're going to use equicontinuity. So beta equicontinuity. There exists a delta such that if the distance between x and y is smaller than delta, then the distance between fnx and fny is smaller than epsilon for all n. Okay, so now we're going to recall a fact from one of your homework problems. So way back when we were doing topology, we showed that if you have a compact metric space then there exists a countable dense subset E inside of K. I think this is a Homer problem. I don't remember. I think it was. Okay, so we get a countable dense subset inside of our compact set. Okay. And remember what we did last time? We showed that if you have that we are guaranteed a pointwise convergent subsequence, right? As long as your set was countable, right? As long as your set was countable and bounded, right? As long as your set was countable and I think it's just pointwise bounded, isn't it? Yeah, it's just pointwise
countable.
Yeah.
You guarantee that.
Yeah. We just needed pointwise boundedness. Well, here we actually have uniform boundedness, so it's even better. Okay. So what do we get? We know that there exists a subsequence fnk that is pointwise convergent on E. I think yes.
I was just going to ask, that statement you just wrote, did that follow from the fact?
So this is the fact, and then by theorem from last class. From theorem from last class, we know that there's going to be a pointwise convergent subsequence. I think I'll put this up. Let me stop here. I'll do it at the beginning of next class. I could probably squeeze it in, but I don't want to just squeeze it in. There's no point, and there's no point in rushing. Okay, so let's start. We'll start at the beginning of this proof of the second part next time.